We had discussed the center of mass of a collection of particles. Now we want to talk about a theorem. The kinetic energy of a system Now, we have summation mi times r center of mass is equal to summation that defines the center of mass coordinate. If we take the derivative of this with respect to time, we get so we define something called the kinetic energy of center of mass. Definition: kinetic energy of center of mass is equal to 1/2 mass, as if the total mass is 1 point, times the velocity of center of mass squared. So this is, you consider all the masses concentrated at the center of mass as if it were one particle, and it moves with the velocity of the center of mass. So this is the definition of the kinetic energy of the center of mass. Kinetic energy in center of mass definition: kinetic energy in center of mass. That means you think of yourself as moving with the center of mass, and then all the particles are moving relative to the center of mass. So in that center of mass system, what's the kinetic energy? It's 1/2 summation mi times vi minus the center of mass. This is the kinetic in center of mass system. Does everybody understand this point? Every particle moves in the center of mass system with this velocity. So in the center of mass system you get this. Now we expand this. It becomes 1/2 sum of mi vi squared minus summation mi vi dot v center of mass plus 1/2 sum mi v center of mass squared. This first term is the kinetic energy. Of the original system. This term becomes, this is sum of m times v center of mass dot v center of mass plus, but these two terms are exactly the same except for a factor of 2. So what we get is the kinetic energy minus 1/2 sum of mi V which is equal to kinetic energy minus this expression is the kinetic energy of center of mass by definition. So if I now move this onto this, we have a theorem. Theorem says the total kinetic energy, which is this term, is equal to the kinetic energy of the center of mass plus the kinetic energy in the center of mass system. Total kinetic energy is equal to kinetic energy of center of mass plus kinetic energy in center of mass system. Everybody happy? Chapter 10. Impulse. If I have a block here which is moving with a velocity, if I now hit it, say I hit it with a force, I give it a strong force for a short period, then it would begin to move in this direction. So its momentum has changed. The original momentum, initial momentum, is equal to mass times the initial velocity. Final momentum is equal to m the difference equal the vector is defined to be the impulse. Now dp dt is equal to the external force. So dp is equal to f dt. If I integrate both sides, the left side is final p minus the initial p, and that is the impulse. So the impulse is equal to this. So we define the impulse to be the change, the total change of momentum. But because of the Newton's law, this says impulse is equal to integral f dt during that period. So if you have a force which starts with 0, it goes to a maximum, then it dies down. Like if I hit this table, if you integrate that force, integrate the vector over time, that result is the impulse. So the impulse can be defined either through the integral of f dt or defined through the difference of the momenta of the particle after and before. The two are the same because of Newton's law. Completely inelastic collision. In a completely inelastic collision, the two bodies got stuck together, 粘在一起。But Newton's law still holds, so the total momentum is not changed. So therefore we have P1 V1, M1 V1 plus M2 V2 is equal to M1 plus M2 times V. In other words, V1 prime is equal to V2 prime. We call it V. But this V is of course also the center of mass velocity. By definition, you look at the formula. So in a completely inelastic collision, namely the two got stuck together, the final velocity is in fact the original velocity of the center of mass. The original V Everybody happy? Any questions? Out of that statement we have immediately a theorem, namely the kinetic energy in a completely inelastic collision always diminishes. Why? Let us use the theorem we just proved 10 minutes ago. We said that the total original kinetic energy is equal to the center of mass kinetic energy plus the kinetic energy in the center of mass system. Now if the things sticks together, then in the center of mass system, finally everybody has the same velocity. So in the center of mass system, the final particles have no velocity. And therefore that theorem, we had a theorem, total kinetic energy is equal to kinetic energy of center of mass plus kinetic energy in the center of mass system. If the particles stick together and move with the center of mass velocity, then of course they are not moving in the center of mass system. So therefore this part is zero. So sorry. in the original system, we have both of these two. In the final system, this part is zero. So therefore, the final kinetic energy is less than the initial kinetic energy. Is everybody happy with this? Thus, the total initial kinetic energy is bigger than the total final kinetic energy in such a system, in such a collision. Because both the initial and final, the kinetic energy of the center of mass system is not changed. But the kinetic energy in the center of mass system at the beginning is a positive number. At the end is zero. So therefore kinetic energy is lost. What happens to that kinetic energy? When we learn the laws of thermodynamics, we know that kinetic energy is lost, but the total energy is not lost because it becomes heat energy. So if two bodies collide with a very large velocity, and get stuck together, it will become hotter afterwards. By the way, that theorem that we proved, that the total kinetic energy is equal to the center of mass kinetic energy plus the kinetic energy in the center of mass system, is a very important theorem. That theorem is not stated in the book. It's the book probably thinks that's a little bit too complicated, but actually it's very simple. Let us now talk about a special case that there is only one dimension. And let us first talk about the case where originally V2 is zero. In other words, we are talking about two bodies. This one is at rest, this one is moving. In that case, it's particularly simple. So we have M1, V1, that's the total momentum of the initial system, is equal to M1, V1 prime plus M2, V2 prime. If it is elastic, this formula is, this first conservation of momentum is always correct. It may or may not be elastic. If it's a billiard ball colliding with each other, it's almost 100% elastic. But if it's two mud balls, then they might even stick together, so it's inelastic. Now let us talk about the billiard ball case, the elastic case. If it's elastic, then the total energy is conserved. So we have M1 V1 squared is equal to 1/2 M1 V1 prime squared plus 1/2 M2 V2 prime squared. So if the initial velocity is known, if V1 is known, then we have two unknowns, V1 prime and V2 prime. We have two equations. So we can solve for the 2. In this particular case, the solution is particularly simple because we can write the first equation as V1. You can do this in any number of ways. A simple way is this. I first move the momentum equation into this form, and I move this part over, and I get M1 V1 minus V1 prime times V1 plus V1 prime is equal to 1/2 M2 V2 prime. I merely rewrote these 2 equations, but now this is very convenient because I can divide the 2. If I divide the 2, I get V1 plus V1 prime is equal to V2 is equal, sorry. Now I substitute that in there, I have eliminated the V2 prime. So V1, M1, V1 minus V1 prime is equal to M2 V1 plus V1 prime. So now I have only one unknown, V1 prime. So I get V1 prime is equal to M1 plus M2 M1 minus M2 V1. This in the book is equation 1030. Once I have V1 prime, I easily get V2 prime, and that turns out to be M1 plus M2 2M1 V1. That's 1031. Case 2, V2 prime, V2 is not equal to 0. Now we talk about the general case. 2 bodies colliding, each of them with a non-zero velocity. So we have V1, V2, and V1 prime, V2 prime. Now let's introduce a new notation. So we have V1, V2 going into V1 prime, V2 prime. Let us now look at the velocity of the defined. V1 prime minus V center of mass. Center of mass velocity is not changed. We have already proven that. So let us call that V double prime. So now we have V1 double prime, V2 double prime. These are V1 prime and V2 prime, but looked at in the center of mass system. That means it's equal to the v1 prime and v2 prime minus the center of mass velocity. So now let us try to ask what is the conservation of momentum. The conservation of momentum means that the original kinetic energy, the original momentum, I claim m1 v1 double prime plus m2 v2 double prime is equal to 0. Because you just take this equation, you take m1 v1 plus m2 v2 equal to m1 plus m2 v center of mass. You move this onto the left side and separate those two terms, you get this. What does that mean? That means that the two velocities if m1 is equal to m2, that means that they are opposite of each other. That means v1 double prime is equal to minus the v2 double prime. Similarly, originally in the center of mass system, I think it's actually easier if I say it in words. Originally, two bodies are colliding. Let us now look into the center of mass system. In the center of mass system, we have these two particles colliding, and in the center of mass system, the first particle, P1 plus P2, in the center of mass system has to be equal to 0. So P1 is equal to minus P2. Finally, P1 is also equal to minus P2. And if the total kinetic energy is not lost, if it's an elastic collision, that means 1/2 m1 p1 squared plus 1/2 m2 p2 squared is not changed. Okay, let's first deal with the case where m1 is equal to m2. So in the original system, in the center of mass system, you have a particle with the velocity coming, but P1 plus P2 has to be equal to 0. So therefore, it's P1 is equal to minus P2. In the final system, the center of mass kinetic energy is also not changed. So can somebody tell me what happened? Originally it's P1, this is minus P2 is equal to minus P1. What should P1 double prime be afterwards? Just think of the center of mass system. You have two bodies colliding with equal mass and opposite velocity. Afterwards, it's still two bodies and still have the equal velocity, and the kinetic energy is not changed. So can anybody tell me what is P1 double prime? It has to go back. So P1 double prime is equal to minus P1. In other words, in the center of mass system, for two bodies with equal mass, in the center of mass system, you have this collision. In the center of mass system, after the collision, they each go out with the same velocity as originally, only change sign. How do I know that it has to be equal in magnitude? Because otherwise the kinetic energy is lost or gained. If the kinetic energy is not changed, the two must have the same velocity. In other words, in center of mass system, the bodies each were turned back with no loss, with no change of speed. Speed means the absolute value. Is that crystal clear, or you still have you can prove this algebraically by writing down the formula, but we don't need that. And let me restate. We have proven that the total energy is equal to the center of mass energy plus the energy in the center of mass system. So in an elastic collision, the energy in the center of mass system is not changed, because the energy of the center of mass is always not changed. Therefore, and since we talk about the elastic collision, therefore the energy in the center of mass system is also not changed. Okay, the energy in the center of mass system for two bodies in one dimension means there is P1, P2 colliding, and afterwards it becomes two particles going away. But if the kinetic energy is not changed, then the only thing that it can do is change sign. So therefore we have each colliding, each bouncing back with the same speed, but with the direction change. And if you think a little bit more, you will realize that has nothing to do with the mass. If the two mass, if one particle has a mass which is very small, this is very heavy. It still holds. So in the center of mass system, this is P1, this is P2, and afterwards this P1 changes sign, this P2 also changes sign. Okay. Think a few times more about what I just said until you feel that you really completely understood this. And that should, if you are still a little bit hesitant, first think of the case where M1 is equal to M2. After you have thoroughly understood that, you would understand that it is also true even when M1 is not equal to M2. Now let us generalize that to two dimensions. A two-dimension elastic collision. The lesson is that you should go to the center of mass system, because everything looks simpler in the center of mass system. The kinetic energy is equal to the energy of the center of mass system plus the energy in the center of mass system. The energy of the center of mass system is not changed. Whether elastic or inelastic, it is not changed. So the only possible change is in the energy of the in the center of mass system. If it's elastic, that means the energy in the center of mass system is not changed. So if you have two bodies in two dimensions, you have two bodies colliding. This is P1, this is minus P1. And afterwards, they can go in any direction now. They are not necessarily going this way. They can go this way. But the kinetic energy in the center of mass system is not changed if it's elastic. So if this is P1, this is minus P1, afterwards this is P1 prime, now in the center of mass system, this is P2 prime. What can you conclude? P1 prime absolute value has to be equal to P1. P2 prime absolute value has to be equal to P2. In other words, in the center of mass system, each body can change direction but not change speed. Two-dimensional elastic collision in the center of mass system. Each particle can change direction. But not speed. can have P1 minus P1, P1 prime minus P2 prime, but the P1 absolute value, the P1 prime absolute value has to be equal to the original P1 absolute value. This is the kind of collision that in big laboratories, when people study the collision, let's say between two protons, it's exactly when you have two protons colliding with each other. It could be elastic or not elastic. Sometimes it's elastic, sometimes it's inelastic. If it is elastic, the velocities are not changed in the center of mass system. Only the directions could change. And that's true if you collide a proton with a lambda, which do not have the same mass. Still, you have the same result. Namely, speed is not changed. And that's true, of course, also in 3 dimensions, any dimension. Okay, if nobody has any problems, we'll move on to another topic. We'll move on to chapter 11 and 12. Now the book, I'm not happy with the presentation of chapters 11 and 12 in the book. So what I'm going to tell you now is more advanced than what's in the book. First, I want to prove a theorem. I'll read the theorem to you. In the motion of a rigid body with one fixed point, there is always a straight line through the fixed point which is not moved. If here's a body, a rigid body, and here's a point O, and suppose that point is not moved, and I now move the whole thing. So finally, let's say it goes this way. That point is not moved. What I want to prove is that there's in fact a whole straight line which is not moved through this point. Not only that point, but the whole line is not moved. If that is the case, that means that there is a rotation. The motion is a rotation through an angle theta around an axis. That line which is not moved is called the axis. And that rigid body now not only is not moved relative to that point O, it does not move along the whole line. So the whole thing is a rotation. In other words, this theorem says if a rigid body has one point fixed, then its motion is always a rotation around some axis. So this is what I next want to prove. This proof can go either geometrically or algebraically. So let's first prove this geometrically. Geometrical proof. Why do I always emphasize that there is a geometrical and an algebraic one? Because in fact, either is correct, but you must know both. Because after you have known both, you understand the thing much better. And so now let's first have the geometrical proof. First, let us not only talk about the point, but talk about a small sphere of, let's say, a diameter, radius 1 centimeter around that point. Because that point O is not changed, so that sphere is also not changed. So therefore, consider a sphere S centered around O. O is, I now consider a sphere. If that point is not changed, then that sphere, so S goes into S prime. So S prime is not changed. So now we don't have to think of a body. We think of just a general body. We just think of a sphere. So we have now a sphere S with a center. I now, like a billiard ball, I now move it such that the center is not changed. What I want to, so the sphere becomes S prime. I now want to prove that the difference between S prime and S is that it's just a rotation. So here's a sphere. Yes. Let's consider a point A on it. After rotation, it becomes A prime. Consider a point A. It goes into A prime. So this is like the Earth. You have one point A, let's say Beijing. Beijing goes into, say, Taiwan. Now I cut the line between A and A prime by a plane.你有个球，上面一点到另外一点，我 cut 一个plane bisect perpendicular bisector. Can anybody tell me what is this intersection? What is that called? It's called a great circle. 就像一个赤道一样。这中文叫什么？大圆啊，是不是叫大圆？所以 A 跟 A， 所以北京在这儿，太原在这儿，你这样切一刀，于是就变成了一个地球上面的一个大圆。The plane that bisects AA prime and perpendicular to it intersects the surface of S in a great circle. We call circle 1. OK， 然后我再来另外一个一点 B， 这 B 到了 B prime， 然后 I do the same thing with the B and B prime, then I get another great circle. So I have two great circles. 这两个 great circle 就 intersect 一个 point， 这个 point 叫 N。Now consider B 到 B prime， 然后出来另外一个 circle C2， 另外一个 great circle。Let N be one of the intersections of C1 and C2. C1 and C2 是两个 great circle， 两个 great circle 一定有两个 intersection， 是在 diametrically opposite。我其中随便取一个叫做 N。So we have 3 points, A, B, and N. So A, B, N forms a triangle. A prime, B prime, N forms a triangle. Now, AN 跟 BN 的距离 ，now AN， 我们回到刚才那个图。这个 N 呢是在这个大 N lies on this big circle. This big circle bisects A and A prime. Does everybody agree that AN, the distance AN is equal to the distance A prime N? 你看这图，看图就清楚了。So So we know an, distance an, is equal to a prime n. For the same reason, the distance bn is equal to b prime n. 这是同样的一个 construction， 因为 n 既在第一个 big circle 上，又在第二个 big circle 上，它在第二个 big circle 上 its distance to b and b prime is the same. Of course, AB is equal to AB prime because it's a rotation. A and B are 2 points on the sphere. It's rotated to A prime, B prime, so the distance cannot change. It's a rigid body. So now we have two triangles. The three sides of the first triangle is equal to the three sides of the next triangle. So therefore it's the same. In other words, the triangle ABN and triangle A prime B prime N is the same. All the angles are the same. Now, assume but N is also a point on the sphere. So in the motion, it goes to a new point, and let's call it M prime. I now want to prove M prime has to be equal to N. That means that point is not moved. A, B, N, A prime, B prime, M prime is equal to is A, B, N moved? By definition, A is moved to A prime, B is moved to B prime, N is moved to M prime. So ABN is moved to A prime, B prime, M prime. That's the definition. So now I have just think. I have now similarly A prime, B prime, N is ABN moved. We just said A prime, B prime, M prime is ABN moved. But we just said a few minutes earlier that ABN and A prime, B prime, N are the same. So therefore, it's also ABN moved. You compare these two. A prime, B prime, M prime is the same as the A prime, B prime, N. So therefore, N is equal to M prime. 在那个 sphere 上 A prime 也固定了 B prime 也固定了，它只能有一个 A prime B prime N A prime B prime M prime 都是同一个三角形，所以它的那个顶尖必须是一样的。所以我们证明了，说是 not only is the point O not moved, but we have found a point N which is not moved. So the whole line ON is not moved. I.e. ON is not moved. It is the axis. Is everybody happy? This proof is actually very simple. Go back and think about it. So what have we proved? We have proved that if a rigid body has one point fixed, then whatever its motion is, it's always a rotation around some axis. So now, instantaneous angular velocity. Now we want to introduce the concept of instantaneous angular velocity. If a body, we consider a rigid body which has one point fixed O. So we have a body, let's say x goes to x prime. This motion is by there's an axis, and once you have an axis, of course, you have an angle of rotation, theta, so delta theta. If that motion goes through a time delta t, that is equal to the average angular velocity. Just like a linear velocity. Now I consider a smaller and smaller delta t, just like our definition of the instantaneous linear velocity. So I'm considering, for example, a rotation, a shorter interval of delta t. So it will be in between x and x prime. But that still is a rotation. That rotation may be along a slightly different axis as this one. But that's another strange. In linear velocity, when you define it, there is the direction. When we define in delta t, it moves from this point to this point. In half of a delta t, it moves from here. So the direction of the velocity is changed. It continuously changes. Eventually, when delta t is very small, it goes into the tangent. What I want to say is that for a linear motion, the direction of the displacement changes as delta t becomes smaller and smaller. Eventually, it approaches a fixed point. Similarly here, if I take a delta t, it's a rotation. If I take half of a delta t, it is also a rotation, but the rotation direction, the axis may be slightly changed. However, when delta t goes to 0, it becomes a limiting direction. Just like here, there's a limiting direction. So a limit of delta theta over delta t as delta t goes to 0, that's called instantaneous angular velocity. But it not only has a magnitude, it also has a direction. In other words, I said that when you take t, delta t, it's a rotation like this with an axis We just because of what we just proved, it has an axis. If you take half of delta t, the axis would be slightly different, just like a linear motion. Eventually, when delta t goes to 0, it goes into some direction. So this instantaneous angular velocity not only has a magnitude, but also has a direction. It's called omega. So this is a vector definition of an angular velocity. Omega is a vector. This is the most important thing, and it's not intuitively immediately clear, but you have to be familiar with it. If a body rotates, it has this omega has a magnitude which is defined this way through the limit, has a direction which is the direction of the axis, the limiting direction. But that still is not complete, because the limiting direction has two directions. It can go this way, it can go the other way. And we define it as a right-handed one. In the definition, we choose the right-handed system. There's an axis. The axis can go either way, but we define it such that if the rotation is this way, we define it to be that way. Okay, so that's called a right-handed system. Everybody happy with what I just discussed? So if a rigid body is fixed, it moves with time, then at each instant it is a rotation with an angular velocity which is a vector, and that vector is along the direction of it's not moving, but it's a rotation around it. Now next I want to ask, what is the velocity of every point? Of every point in the body, in the rigid body. What is the velocity of every point in the body? And the fundamental formula is这是 point O， 这是这个欧米伽。O is the fixed point, and we have just defined the angular velocity omega. Now I consider a point R. It's a rotation这个 plane 在这儿有一个 point. This is the if you fix O and take R and go around in a circle around the axis omega, you draw the circle, and this is the center of the circle. 这个 what is the velocity of 这个 point？ 这个 point 是 I claim 是 the v， 这 r 这个 point 这是一个 rigid body， 它要 rotate， 它的这个是等于 omega cross r。First, the direction. The direction of this point, the direction of motion of this point is the tangent of that circle, and that's exactly the direction of omega cross r, because omega cross r is perpendicular to the omega OR plane, and therefore omega cross r is in the direction of the tangent to that circle, and that's of course the direction of the velocity. The magnitude of the velocity of this point is equal to this distance, which is r sine theta, and that's precisely what is in the definition of cross product. You remember that we had the definition of a cross product omega cross r. In that definition, it's the magnitude of r times the magnitude of omega times sine theta. And that's exactly because sine theta times r is exactly this distance, and that distance times the delta omega divided by delta t precisely gives you the velocity. So we have this formula. This you have to understand this so that it becomes a part of your system. It's instantaneously you would remember this. So let's see what we have learned. What we have learned is that if a rigid body moves with one point not fixed, one point not moving, one point fixed, then it has a omega. It has a vector angular velocity, and once you know that omega, you know the motion of the velocity of every point in the body. Now what happens if it's a general motion? General motion of a rigid body. So you have a body here, and it moves to here. I take one point here. So the whole thing is moving and it's rotating. It's obvious that that motion is equivalent to a movement of O to O. You can take any point O. Suppose it moves to O prime. So you decompose the motion into motion O into O prime and the rotation around O. So general motion of a rigid body is equal to a motion of one point just any point followed by a rotation. That point O is arbitrary, but it's the most convenient if we take it to be the center of mass. So we usually think of the motion of a rigid body to be the motion of its center of mass plus an omega around the center of mass. That means we have, in general, a velocity of the center of mass and an omega around the center of mass. So the motion of a rigid body is now specified by two vectors. And the velocity of 任何一个 point 是 equal to the velocity of center of mass plus r cross omega plus omega cross r. R 是 vector position of the point relative to center of mass. What we have just discussed is a very important theorem. We resolve the motion of a rigid body into two vectors, and this formula gives you the instantaneous velocity of every point on the rigid body. We had given a geometrical proof. The key point of the geometrical proof is to show that in a rigid rotation, where one point is not moved, there is always a whole axis which is not moved. We can show this also algebraically. To do this, we need some matrix theory. It's a linear algebra. How many people have learned some linear algebra so far? Nobody? How many people have not learned the linear algebra? 0 plus 0 cannot be equal to 1, so something is wrong. Don't be bashful. Is everybody studying linear algebra now? Yeah. Oh. And have you learned matrix multiplication? Yeah. Okay. Okay, let's go through that once more. I can write the coordinate x, y, z as a column, and let's call it R. In other words, instead of the vector R, I now form it into a matrix. And I have tilde. Tilde is turn the matrix turn this word column into a row. So tilde is equal to. So a matrix which is like this, after you do the tilde, it becomes like this. You take this 45 degree and rotate it in this form. So, what is R tilde R? R tilde R is x, y, z times x, y, z. When you multiply two matrices, you just take this column and multiply this, so it becomes x squared plus y squared plus z squared. Now, let us write ijk. Let us give it a arbitrary symbol. Let's call it x. Now, x r is therefore equal to xi plus yj plus zk. But by definition, when I multiply an x, the r here we can have the arrow. We don't need the arrows. It doesn't matter whether you write an arrow over it. This is a row. This is a column. So it's like this. Now let us rotate the I consider a rotated coordinate system. Call that x prime. So I've originally ijk. I've rotated the coordinate system. I shall call it the I prime, j prime, k prime. And I write it as a row matrix, x prime. Then x prime, r prime is equal to x prime, I prime plus y prime, j prime plus z prime, k prime. And so this is the coordinate. This describes a point. This describes the same point. So therefore they have to be the same. So x prime, r prime is equal to x, r. That means the relationship between x prime and x, and also the relationship between r prime and r are linear. So r prime is a column. Is equal to a matrix which I shall call gamma times r, where this gamma is a 3 by 3 matrix, and this is r prime. I erased this. It's better if we do it in other words. X prime is equal to I prime, J prime, K prime. Now, I prime is a linear combination of I, J, K. And J prime is the new y-axis, is a linear combination of the I, J, K. K prime is a linear combination of I, J, K. So therefore, X prime is equal to X times a matrix gamma. This is a row, this is a row, this is a column. There are 9 elements of gamma. Each element is the coefficient in the expression of I prime or J prime or K prime in terms of I, J, K. If I substitute that into here, I get gamma therefore if I multiply this by the inverse, how do I know that gamma has a inverse? I'll come to that in 1 minute. If I multiply both sides by gamma inverse, I get R prime equal to gamma inverse R. We could have defined gamma inverse by this formula. In other words, R prime is X prime and Y prime Z prime. X prime and Y prime Z prime are linear combinations of X, Y, Z. And so it has 9 coefficients, and that 9 coefficients is gamma inverse. Now, we know that R prime that by definition is X prime squared plus Y prime squared plus Z prime squared. And that's clearly equal to X squared plus Y squared plus Z squared, because that's the distance squared from the origin. So this is equal to R Now I plug that formula in, therefore this side. Now when you take a wiggle of AB, does anybody know how to take A is a matrix. This is more general than what we just looked at. Suppose I have when you multiply two matrices together, A and B, they can both be rectangular. of whatever size, but only there's one thing must match, namely the width of the first one must be equal to the height of the second one. Otherwise, you cannot multiply them, because when you multiply, you always take, let's say there are three elements here, let's say call them alpha, beta, gamma, and this is A, B, C. There is alpha A plus beta B plus gamma C. So this width must be equal to this height. But after you multiply, otherwise there's no restriction, and the result of this has the height of this one and the width of this one. When you multiply A and B, the final result has a height which is the height of A, has a width which is the width of B. And there's a formula of A. When you turn it into a tilde, the theorem is that this is a trivial theorem. It's equal to B tilde times A tilde, but you have to write the order differently. Does everybody know the theorem? Okay, so this becomes R tilde, gamma inverse tilde, gamma inverse R is equal to R. Now let us look at this. Both sides have R and R at the end, and there's something in the middle. This is a 3 by 3 matrix. So this is but this is nothing but x squared plus y squared plus z squared. And here is x, y, z, here's x, y, z. And if you think about it for a few minutes, you immediately know that this has to be equal to 1. The conclusion in that is one is 1, 1, 1. You think of this one. If I sandwich it between R tilde and R, I get exactly x squared plus y squared plus z squared. You may object. You say that it does not yet follow from here that is equal to 1, because what happens if these two elements are equal and opposite? If these two elements are equal and opposite, this formula still holds. But you know that this is a symmetrical matrix. How do I know it's a symmetrical? I tilde it. The footnote. The tilde of this by this rule is equal to the tilde of a tilde is equal to itself, because we return it twice. So that means this thing, after you tilde it, comes back to itself. So that means that the matrix is symmetrical. If it's a symmetrical matrix, you cannot have these two opposite. So therefore, we have this. This is a footnote to prevent the objection that maybe it's a 1 here and minus 1 here. You can't be, because it has to be a symmetric matrix. So that's the most important statement. If a matrix is equal to 1, its inverse is also equal to 1. So I can take the inverse. When you take the inverse of AB is equal to the inverse of B times the inverse of A. again reversed order. So if I take the inverse of this, I get gamma and gamma tilde is equal to 1. So such a matrix is called an orthogonal matrix. Furthermore, the determinant of gamma is 1. Furthermore, how do I know that? First, I take the trivial case of no motion. Then x prime is equal to x, y prime is equal to y, z prime is equal to z. So, we'll go back to this formula. If it's no motion, then r prime is equal to r, so gamma is the unit matrix. Gamma is 1, 1, 1. The determinant of the unit matrix is of course 1. Now I make a slight motion. Because of this, I have the determinant of gamma times the determinant of gamma tilde is equal to 1. But the determinant of gamma tilde is equal to the determinant, because if you have a matrix, if you have a determinant, if you turn it around for the determinant, if you change the rows and the columns, the determinant is not changed. So that means the determinant of gamma squared is equal to 1. So the determinant of gamma is always plus 1 or minus 1. Now, if to start with no motion at all, gamma is equal to 1, so its determinant is 1. Now I consider a slightly changed motion. The gamma cannot suddenly, the determinant of gamma cannot suddenly change from 1 to minus 1. So if I continuously change the rotation, the determinant cannot suddenly change from 1 to minus 1. So the determinant remains 1, and that's why I wrote this determinant is equal to 1. This is a topological proof. And in the mathematics of the 20th century, topology gets married to geometry, to algebra. And what we have shown is just a typical example of that. So the net result, we have the following. We now have a 3 by 3 real matrix, which is orthogonal in the sense that gamma tilde is equal to 1. And furthermore, its determinant is 1. That's called an element of, so mathematically now one says gamma is an element of SO3. O means orthogonal. 3 means 3 dimension. 3-dimensional orthogonal matrix. An orthogonal matrix is one that satisfies this condition. The S says special. Special means that its determinant is plus 1. So the rotation gamma algebraically is an element of SO3. Much of 20th century mathematics consists of generalizations of this. You can go to SO4, you can go to SO5, you can go to SON. You can also generalize it so that it's an orthogonal matrix, but it's not necessarily real. So it becomes complex orthogonal matrix. And such things are, in some sense, is one of the main structures of 20th century mathematics. And what we now find is that all those structures are deeply related to the structure of elementary particles. So we'll come to that in the future. If any of you found that what I discussed today is a little bit too complicated, please come to talk to me this afternoon. I think if nobody comes, then it's better because we can go faster. But if many people come, then we have to discuss what to do. Okay, bye-bye. Good luck.